There is an object at the edge of our observable universe that should not exist. Not in the way scientists use that phrase loosely, as hyperbole for something unusual. In this case, the mathematics of how galaxies live and die, the physics of how black holes grow, the models we have spent decades building, they all say this object cannot be what it appears to be. And yet, in February of 2025, a team of astronomers pointed the most powerful space telescope ever built directly at it, and what they found didn't calm the problem. It deepened it. Its name is PhoenixA, and it may be the most extreme object the universe has ever produced. To understand why PhoenixA matters, you need a number, 100 billion. That is the estimated mass of the object at the center of the Phoenix cluster, expressed in solar masses, meaning 100 billion times the mass of our own sun compressed into a single point in space. For comparison, the black hole at the center of our Milky Way, Sagittarius, a star, the one the Event Horizon Telescope photographed in 2022, weighs about 4 million solar masses. PhoenixA is 25,000 times more massive than that. It sits in a cluster of galaxies 5.8 billion light-years away, in a system so massive it is among the heaviest galaxy clusters ever catalogued. Yale astronomer Priyam Vada Natarajan has proposed that 100 billion solar masses may be the hard theoretical ceiling, the absolute maximum a black hole can ever reach before the universe itself conspires to stop it growing further. If she is right, we have found the largest black hole that will ever exist, and in early 2025, it appears to have woken up. The Phoenix cluster was discovered in 2010 by MIT astrophysicist Michael McDonald using the South Pole Telescope, an instrument designed to scan the sky for distortions in the cosmic microwave background. What McDonald found wasn't subtle. The cluster was blazing. 2 years later, in 2012, follow-up observations confirmed something that made the astronomy community sit up. The galaxy at the center of the Phoenix cluster was forming new stars at a rate of 500 to 800 per year. To appreciate what that means, you need another comparison. The typical large galaxy cluster produces roughly 1 new star per year in its central galaxy. The previous record holder was forming about 100. Phoenix was doing 800. It was so far beyond every other known system that it was almost statistically invisible, an outlier so extreme it barely registered on the charts scientists used to compare these objects. The question was simple: why? And the answer has to do with something physicists call the cooling flow problem, a mystery that has haunted cosmology for 4 decades. Here is the basic mechanism. At the center of galaxy clusters, there is a vast reservoir of extremely hot gas, superheated to tens of millions of degrees, called the intracluster medium. Physics dictates that dense hot gas should cool over time. As it cools, it should flow inward toward the central galaxy, feeding it and triggering star formation. This is a cooling flow. But when astronomers looked at cluster after cluster across the universe, they couldn't find the evidence. The gas wasn't cooling. The stars weren't forming at the predicted rates. Something was reheating the gas before it could collapse. The prime suspect was the central black hole itself, firing jets of energetic particles that acted like a thermostat, constantly pumping heat back into the system, suppressing the very star formation it should have been enabling. It was a feedback loop of cosmic proportions, and it seemed to work everywhere except Phoenix. Phoenix appeared to be the exception. Its black hole, PhoenixA, seemed to have lost the battle against its own cooling flow. The gas was cooling, the stars were forming, the thermostat was broken. But for over a decade, no one could explain why, because no telescope had been able to see the critical evidence. The intermediate temperature gas that would exist if a true cooling flow was actually taking place. Hot gas radiates in X-rays, detectable by observatories like Chandra. Cold gas glows in visible wavelengths visible to Hubble. But the transitional gas, cooling through a range of roughly 300,000 Kelvin, emits in the infrared at wavelengths that no previous instrument had the sensitivity to detect at this distance. That is until JWST. In February 2025, MIT graduate student Michael Reefe and his collaborators published a paper in Nature detailing the first direct imaging of a cooling flow in any galaxy cluster in history. Using JWST's ability to detect a specific infrared emission line called NE6, which traces gas cooling through exactly that intermediate range, they mapped the warm gas at the center of the Phoenix cluster and found it everywhere, not in isolated pockets. Everywhere they looked, there was a halo of intermediate gas cascading through the temperature spectrum from superheated to cold, feeding directly into the regions where stars were being born. For the first time, we have a complete picture of the hot to warm to cold phase in star formation, Reefe said, which has really never been observed in any galaxy. The cooling flow was real. PhoenixA had not been maintaining its thermostat. It had let the temperature drop. And now, billions of stars were being born in the aftermath. But here is where it gets unsettling. The black hole is not simply dormant. The same observations that confirmed the cooling flow also revealed something else. PhoenixA is firing jets, enormous radio jets, energetic enough to carve out vast bubbles in the surrounding hot gas, pushing it sideways, reshaping the environment. The black hole is active. It is producing feedback. And yet the cooling is still happening, still generating stars at a rate no other cluster can match. PhoenixA appears to be doing both things simultaneously, heating the gas with its jets and failing to stop the gas from cooling. It is caught in a state that no model fully predicted. McDonald himself said it plainly, "We understand pretty completely what is generating all these stars. We don't understand why." This is not the first time a single anomalous object has forced cosmology to reconsider its foundations. In the 1960s, astronomers using early radio telescopes began detecting objects of impossible brightness, so luminous they outshone entire galaxies, yet apparently point-like in size. They were called quasi-stellar objects, quasars. For years, the debate raged about what could produce that much energy. Some proposed exotic new physics, others suggested errors in measurement. The resolution that quasars were supermassive black holes consuming matter at prodigious rates in the early universe took decades to fully establish, and in doing so, it rewrote our understanding of galaxy formation entirely. We now know that virtually every large galaxy has a supermassive black hole at its center, and that the coevolution of those black holes and their host galaxies is one of the central stories of cosmic history. PhoenixA may be doing something similar, pointing to a regime of black hole behavior that our models don't yet accommodate. Closer in time, the cooling flow problem itself was once considered essentially solved. In the 1990s, before the launch of the Chandra and XMM Newton X-ray observatories, Theorists had built elaborate models predicting enormous quantities of cold gas accumulating at the centers of clusters. When Chandra launched in 1999 and looked at these systems in detail, the cold gas wasn't there, at least not in the predicted quantities. The cooling flow model was dramatically revised. The black hole feedback explanation became dominant. That explanation now accounts for nearly every cluster in the observable universe, every cluster except one. So what is actually happening at the heart of Phoenix? There are at least 3 serious interpretations, and none of them is fully satisfying. The first is that PhoenixA represents a temporary phase, a brief window in cosmic time when the feedback mechanism has simply fallen behind. In this view, the black hole's jets are real and active, but the density of the cooling gas in this particular cluster is so extreme that even powerful jets cannot reheat it fast enough. The cooling flow is winning temporarily, and eventually PhoenixA will grow massive enough, or its jets powerful enough, to restore equilibrium. The problem with this explanation is the time scale. The Phoenix cluster appears to have been in this state for a significant fraction of its history. A temporary imbalance lasting billions of years strains the word temporary. The second interpretation is more radical. It holds that PhoenixA is not simply an overachieving black hole, but an object in a genuinely different class, what some theorists have begun calling a stupendously large black hole, a hypothetical category beyond ultramassive, governed by physics that standard models do not yet describe. If PhoenixA has truly reached the theoretical ceiling of 100 billion solar masses identified by Natarajan and colleagues at Yale, it may interact with its environment in ways that no simulation has yet captured. Its gravitational influence alone spans a region larger than most galaxies. Its behavior may not be predictable from anything we have observed before. The third possibility is the most philosophically challenging, that the cooling flow problem was never really solved, and PhoenixA is simply the cluster extreme enough to expose the gap. In this reading, black hole jets suppress cooling in most clusters not because the physics is well understood, but because most clusters are not as massive or as dense as Phoenix. The models work for the average case. Phoenix is not the average case. And if that is true, then the question Reefe and McDonald are now asking, why this system, may have an answer that forces us to rebuild our picture of how the largest structures in the universe regulate themselves. The science is open, the data is real, the explanation is not yet written. There is something worth sitting with in all of this. We found PhoenixA, not because we were looking for an anomaly, but because we were doing ordinary science, scanning the sky, cataloging clusters, following up on brightness measurements that didn't quite match expectations. A hazy blue circle in a Magellan telescope image in 2010. That was the beginning. 15 years later, JWST is mapping the invisible architecture of a cooling flow around the largest black hole that may ever exist. And the people doing that work are not claiming victory. They are saying they don't yet understand why. That intellectual honesty is not a weakness in science, it is the whole point. The universe is not obligated to be simple or to arrange itself into systems that conform to the models we build in the limited time we've been looking. PhoenixA has been doing what it does for billions of years, long before there were eyes to see it. long before there was a species capable of pointing an infrared telescope at a galaxy cluster 5.8 billion light-years away and asking what temperature the gas was. The fact that we can do that now and find something we cannot explain is not a failure. It is the frontier. If PhoenixA is truly at the ceiling, the largest black hole the universe will ever make, then in some strange sense we are living through a privileged moment. We exist at a point in cosmic history when that object is still there to be studied, still close enough to observe, still active enough to reveal itself. In another 100 billion years, the stars it is currently forming will have lived and died. The cluster will have dispersed. PhoenixA itself, starved of fuel in an expanding and cooling cosmos, will have gone silent. We happened to arrive while it was still speaking. The question is whether we are listening carefully enough to understand what it is saying. Thanks for watching, and subscribe for what we discover next.